Socials to start with here. Okay, who's this guy? René Descartes in French. Okay, in 1637, was that like a long time ago? It's a relative way of speaking. That's only like 5 generations. So your great-great-great-grandparents, like, okay, they didn't do this stuff in school. They didn't even have school, right? Threw them out in the farm and said, there's your school. This guy invented this stuff, okay? We're not doing socials. I'm not going to read too much about it, but the Cartesian plane, that's this, okay? Oh, okay, now I know what he's talking about. Yeah, when you graph points, that's what we're talking about. That's the Cartesian plane. He's the first guy that came up with a system saying, let's make x this dimension, let's make y that dimension, and then we can plot them in a 2-dimensional space. Some of you are wondering, hey, when do I get to 3D? Yeah, there is a z-plane that goes in and out of the page, okay? You're not going to see that till university, okay? So, just flat, 2-dimensional, Galileo, flat Earth, right? You sail too far in your boat, you fall off the edge. Don't go out there, it's scary. Okay? So, this is the Cartesian plane. We've done this, right? We got 2 axes. The dead center, that's called the origin, usually noted by an O. Hey, there it is. What's the coordinates of the origin? 0, 0, yeah, okay, we've done this before, good. Any coordinates we write as an ordered pair, like that. It's always, always, always bracket x coordinate, comma, y coordinate, bracket. Okay, that's an ordered pair. That's how we write coordinates. Okay. X is always first. Always, always, always. Y is always, of course, second. That's the only 2 you have, right? There's quadrants here. There's a quadrant. Okay. Here's a quadrant. And where's another nice color? There's a quadrant. And do I have another nice light one? There's a quadrant. 4 quadrants. Note the word quad means 4. Anyone ride a quad? How many wheels does it have? You what? You got to go and screw it up, huh? All right. You and your Russian-made ATV with 7 wheels on it. Where's the 7th one? On top of your head so you can spin it. Okay. These are quadrants. This is how we name them. Quadrant 1, Roman numeral. Quadrant 2, Quadrant 3, Quadrant 4. I don't know why someone went counterclockwise when they did this, right? That's the opposite direction that the hands on the clock go. See this one up here? In 100 years, this will be like clockwise will have no meaning, right? It'll all be digital. Okay, but that's how we got to do it. Counterclockwise, we go in this direction. 1 starts here. This is the positive quadrant, right? Everything in here is positive for x, positive for y. Okay, and then 3, then 4, and then we're back to 1 again, okay? Complete the following by writing the coordinates of these points. So point A, how do I get there from the origin? I go 1, 2, positive direction of x, bracket, 2, comma, what's y? 1, 2, 3, 4, positive direction. So that's the coordinates of point A. Is this new for anybody? Were you all seen it before? Okay, nobody's going to admit if it's like, oh, whoa, what's that? What's he doing? Okay, B, where's B? That's over here. It's right on the x-axis. It's always x first, okay? So to get there for x, I go 1, 2, 3 in the negative direction. Okay, if that's positive, left is negative. And then what's my y position? How far do I go up or down? I don't go anywhere. But a coordinate pair always has two coordinates, so you have to write 0. Okay? That's the coordinates of that point. -3 for x, 0 for y. C, how do I get over there? I go 1, 2, 3, 4, 5, 6, and then down 1, 2, 3. Down is negative, so that's -3, right? Okay? D, that's right on the y-axis. Where do I go for x to get down there? Straight down. I don't. Okay? X is 0. I don't go left. I don't go right. That's it. I just go down 1, 2, 3. So the coordinates of D is 0, -3. Point O, that's the origin. What's the coordinates of that again? Yeah, I don't go anywhere for x. I don't go anywhere for y. I just stay there. That's the coordinates. Okay? Don't just put 0. I'm going to ask you, is that x or y? Okay, you got to have x, comma, y. All right? Write the coordinates of the point in the second quadrant. There's only one point in the second quadrant. That's E. What's the coordinates? X first. -2, comma, and 1, 2, 3 up. Right? What's the point in the third quadrant? That's P. How do I get there? Well, I go -1, -2, -3, -4, and I go down 1, 2, 3. All right? That should be review. If that's like, what's he doing? You'd better come in and ask, okay? Oh, yeah. No, it's supposed to be review. Okay, thanks. Yeah, negative down, right? Okay. Quadrant 1. Complete the following using positive or negative. In quadrant 1, is x coordinate positive or negative? Positive. I already kind of said this. Always, always, always. Y in quadrant 1, that's also positive, isn't it? In quadrant 2, for x, it's always negative, right? I'm always going to go to the left to get in quadrant 2. But for y, it's always positive. Quadrant 3, it's going negative for x, negative for y. That's like the opposite of quadrant 1. Quadrant 1's positive, positive. This one, it's always negative, negative, right? And then quadrant 4, I go positive for x, and I go negative for y. Okay? That always happens. Never changes. Okay, let's look at a relationship. What's the name of this chapter? Relations. Okay? Not like family, like that's my mother and that's my third cousin twice removed type stuff. We want math relations. How does something compare to something else? Anyone done this? Maybe with cards? Oh, you guys don't do that anymore, do you? You all got your gadgets. Okay, toothpicks. This is a toothpick. Something you use to clean your teeth with after chicken. Okay, can you make triangles with these? Depends how many you have. You're not allowed to break a toothpick, okay? Can't. Calvin, don't even think about it. How many toothpicks do you need to make a triangle? We need 3. What kind of a triangle is that? With all sides equal, equilateral. What's the size of the angle in an equilateral triangle? 180 degrees. If they're all the same, yeah, 60 degrees. Okay, just let's do a little review as we're going. All right, a second triangle is formed. Here's the original triangle. How many more toothpicks do I need? I need 1, I need 2 more to do 2 triangles. Okay, here's my original triangle. There's the second triangle. How many more toothpicks do I need to get the third triangle? 2 more. Do we see a bit of a pattern happening here? Yeah. If you were in grade 3, I would say, okay, kids, I got 60 toothpicks. How many triangles can you make? Everyone's all super. They start making them, right? By the time you get to grade 10, we should be going, let me just do the first 3. Let me figure out with math how many I can make, because I know a pattern here. Okay, maybe you're going to make yourself a little table. Let number of triangles be t. Let toothpicks, now this is a bad one because they both start with a T, so they're going to let toothpicks be P, okay? And then we got toothpicks and triangles. One of them's got to be a different letter. Okay, 1 triangle, I need 3 toothpicks. 2 triangles, how many toothpicks? 3 and 2 is 5. 3 triangles, I have 5, and how many more? Yeah. 4. How many do you think I'm going to need? Do you see a bit of a pattern happening here? Sure. Okay. So, and hopefully, like in grade 8, maybe you'd like, if I said to you, all right, you have 47 toothpicks, how many triangles? Some kids would like make their table all the way up to 47 and C, okay? We got to get away from that. We're going to come up with a little formula that relates this and this. Okay? So, represent the data from the table of values on the grid. Graph. That's what they're saying. So quickly, here's triangles. They put it down here. Toothpicks is here on this axis. This is like your y, but it's not y anymore, it's p. Okay? This is your x, but it's not x anymore, it's t. How many quadrants are in this graph? Just the positive quadrant, right? Does negative triangles make any sense? No. Negative toothpicks? That doesn't make any sense. So I don't want quadrant 2. I don't want quadrant 3. I don't want quadrant 4. Okay, I just want the positive quadrant. That's the only one that makes sense here. Okay, so they've kind of made it nice for us. I go from 1 to 5. So you want to go 1, 2, 3, 4, 5. That works. Okay, starts at 0, of course. This goes up to 11. So this one's kind of nice. We're just going to go 1, 2, 4, 6, 8, 10. Okay, then just plot it. You always want to look at your data before you start throwing down numbers, because you got to make sure you have enough, right? This thing's going to go up to 11. That's going to be fine. Never break your graph. You guys remember that from grade 8? Don't distort your graph by going, well, I'm going to start it at 6. Then your line's going to look like this. Does that look like a line? No. So always consistent along your axis, okay? So 1 is 3. There it is. 2 is 5. 3 is 7. Does it kind of look like a line starting to form here? 4 is 9. That's here. And 5 is 11. Okay, but don't make it a line. Explain why in a sense. Oh, look. D. Explain why it does not make sense to join the points in a straight line. Well, I'll explain. If I did that, don't do this, that would imply that this right there makes sense. What does that point mean? Triangles. I got 3 triangles, 4 triangles. That's about 3.5 triangles. Does that make any sense? It doesn't. And how many toothpicks do I need to make 3.5 triangles? About 8.2. Calvin, I said you couldn't break them. You can't have a quarter of a toothpick. Okay? That's why it doesn't make any sense. Those points make sense, the line does not. You don't know what this means yet, but it'll be explained in the next page. The data is discrete, not continuous. Okay? Another word is intermediate values make no sense. In other words, in between those dots, it has no meaning. You either have a triangle or you don't. You can't have a half a triangle. Okay? This is on page 392. We'll see that in a sec. Okay? Describe in words the relationship between toothpicks and triangles. Well, let's go back to our data table. Like I was saying, if I said to you, you have 21 toothpicks, how many triangles can you make? You might just go up here and go, well, you know, let's make our table up to that point. And yeah, you could do it. But if I said to you, you have, I don't know, 501, do you really want to do that? No. What's the relationship between here and here? How do I get from 2 to 5? How do I get from 3 to 7? What do I do? In words. Add 3. Okay, let's see if it works. 3 and 3, that doesn't work. How do I get from 4 to 9? Alicia. Double it and add 1. Let's see if it works. 5 times 2 is 10 plus 1. Is that 11? Okay, let's check another one. 2 times 2 is 4 plus 1. Is that 5? Sure. Okay, so if I had 501, I would just do reverse. If I subtract 1 from 11 and get 10 and half it, I get 5. If I subtract 1 from 501, I get 500. If I half 500, how many triangles is that? Well, that's easier than making a table up to 501, isn't it? Okay, there's a pattern. That's why it makes like a line, but don't make it a line. Okay, what's the relationship between toothpicks and triangles? Okay, toothpicks is double the number of triangles, and then what? Add 1. That's it in English. Okay? You got to see a pattern here. If it doesn't make a pattern, it's not going to be linear. It's going to be like scattered. Maybe it's going to make a curve. Okay? But guess what? The only thing you guys are doing in Math 10 is linear relationships. Okay? That's it. You don't get curvy until you get to grade 11. So let's take the words and make it just numbers and variables. Let's take the word problem and make an equation with it. You remember how fun this was in the last couple questions in factoring? Okay, well, it's not going to be quite that hard. Write an equation that can be used to determine the number of toothpicks if we know the number of triangles. I worded this really, really nicely. Toothpicks, what's our symbol for toothpicks? P. Okay, P is double 2 times the number of triangles, add 1. There's equation, an equation. That can help us solve anything you want to throw at it. If I said to you, I need 87 triangles, then you should be able to tell me how many toothpicks I need. Put in 87 right here, double it, add 1, you're done. If I said to you I had 9,071 toothpicks, you put that number here, okay, and you solve that using algebra. Which brings us to G. Use the equation to determine the number of toothpicks if there's 27 triangles. Because my graph only goes to 5. Maybe I could squeeze in 6. Does it go to 27? No, I can't find that point. Does my data table go to 27? Triangles, sorry. No, it doesn't, right? But I got an equation. So that's what I'm going to use. 27 triangles, I'm going to plug that right in there. What's a math word for plug? Substitute. I'm going to substitute this number in here. How many toothpicks do I need? What's 2 times 27 plus 1. 54 plus 1, I need 55 toothpicks. Okay? What if I have 83 toothpicks? Okay, smart kids are already going, well, 83 minus 1 is 82. What's half of 82, Tyrell? Yeah, but we got a formula. Okay, I got 83 toothpicks. That's P. Substitute that in there. That's 2 times T plus 1. How do I solve this little grade 8 algebra question? I want T by itself. I want to know how many triangles. I got to get rid of this 2. I got to get rid of this plus 1. It doesn't matter which one you do first, but it's always easier if you get rid of the add or subtract one first. Okay? How do I get rid of plus 1? Minus it. Always the opposite operation. Okay? The opposite of plus is minus. And it's gone. 83 minus 1 is 82 is 2t. How do I get rid of the 2? Yeah, it says 2 times t. So I want to divide it away. What's 2 divided by 2? Don't say 0. It's not 0, it's 1, right? 1 times t is t. Whatever you do to one side, you got to do to the other side. T is, I can make 41 triangles. There's math for triangles. If I have 83 toothpicks. Okay? That's a little quicker than maybe trying to make triangles with them, with the toothpicks. Okay, that's what you do in elementary, right? Okay? How are we doing? Tons of time. All right, this is my bread and butter. Physics. If Liam sticks his finger in that socket over there in the wall, did he know the amount of current and the amount of voltage are related? Or did he just get electrocuted and he doesn't care? Yeah, probably the latter. Depends how his conductivity of his finger is, right? You might just get a little, whoa, that was cool, and then you'd be good, but don't do this, okay? They are related. Students in a physics classroom determine the resistance in an electrical circuit by measuring voltage, V, and current, I. And you guys did this formula in Science 9 too, right? It's called Ohm's law. There's a relationship between voltage, current, and resistance. Okay, anyway, this is what he got. He hooked it up with a meter, a little variometer, and changed this current, and that's how much voltage he got. He got that much, he got that much, okay? This much amperage, that's current, that's how much voltage he got. Represent the data from the table on the grid. Graph. Okay, this one's a little harder to figure out. We're going to put current down here. We're going to put voltage here. Okay, what's this thing called again? Named after René Descartes. Cartesian coordinate system, yeah. And of course, that's just the positive quadrant. There's no negative voltage. It doesn't make any sense, right? Not yet. Okay, so what do I want to do here? I got current I goes from 1/2 up to 4. Do you want to do this? 1, 2, 3, 4. Hey, I'm done. No, that's not how you graph. Okay, I got lots of lines here. See the kind of bolder ones? If I go 1 there, 2 there, 3 there, 4 there, that's a good way of using the whole graph that's given. Okay, because if this was Physics 11, you guys, some of you taking this next year with me, if you don't use at least most of the grid, I'm going to be taking marks off. Okay, voltage goes up to 48. So you don't want to go 1, 2, well maybe it does work, okay, but you got to check. Does it work if I go 1, 2, 3, 4, 5, 10, 15, 20, 25? No. Going to run out of real estate. Okay, so how could 50 would be nice. How about each line is 2? Does that make sense? 2, 4, 6, 8, 10, 20, 30, 40, that's 50. Perfect. Okay, don't write the number on each one. That's a waste of your valuable time. Now, 0.5 is 6. 0.5 amps, that's halfway between 0 and 1, is 246. So that's right there. Everyone agree? Okay, 1.5 amps is 18 volts. So 1.5 is 18. Do you think this is going to be a linear relationship between current and voltage? What other relationship am I going to give you in Math 10? 3 is 36. So now we're right on 3. That's 30, 2, 4, 6. Does that kind of look like they're in a line? 3.5 is 42. And finally, 4 is 48. Now that's 50, that's 48. Okay? Kind of look linear? Even with my distorted projector, does that kind of look like they make a linear relationship? Now, do we want to join this line? Emily thinks so. Could I have, like this thing, he found this measurement. 3 amps is 36 volts, okay? Is there some value of 2.5 amps I could draw out of that thing? Why not? Is there like 1.1 amps out of there? Sure. This thing, if you measure it on a dial, it'll draw as much current as you want. It's infinitely adjustable, just like most volume controls on your radio. Okay? Some volumes, yeah, they have notches and they go from here to here to here. That would be discrete. If it's digital, that's discrete. But good old analog dials, it's infinite how many you could possibly have. It makes sense to draw a straight line here. Okay? Yes, explain. Well, we're going to use the word continuous. And I hope, what was our last thing? Intermediate values. Here they make sense. All right? Now the maximum you can get out of one of these sockets is 15 amps. Okay? Because if it exceeds that, it flips the breaker. And those are just right over there. Okay? And that's for safety. But it's infinite. Like some appliances you plug in, they'll draw 9 amps. Plug in my wife's hair dryer and it's like 14.99 and it flips the breaker when my daughter turns the TV on. Okay? There's a little appliance, maybe you're going to charge your iPod. Maybe it's only 0.01 amps. There's infinite amount of current that can come out of that little switch. Okay? It's continuous. Intermediate values make sense. I could have this point, that point, this point, right? Every single one. Okay? Use the graph to determine the voltage for a current of 2.5 amps. Let's say I plug in something and it draws 2.5 amps. Use the graph. Well, look. Here's 2.5 amps. What is the corresponding voltage? Where does this thing cross that line? You just look across, okay? That looks like it hits about there. What does that look like? Well, that's 28. Let's call it 29, okay? So that's what it kind of looks like. It should be 30, I know from the relationship, but I didn't draw a real careful line here, did I? I just did it rough, okay? So let's say that's about 29 volts. If I gave you any value of current on here, could you tell me the corresponding voltage it draws? Sure. All you do is cross it off. But what happens if it's off my graph? What if I said, okay, my wife's hair dryer, that's 14.9 amps. What's the corresponding voltage there? It's off the scale. That's where the formula comes in handy. Okay? Because I don't want to keep going to my graph here because I'm going to run out of paper. Write an equation expressing V in terms of I. We go back to our table. How do I get from here to here? Who sees this relationship? And you don't have to look at that number. Maybe it's easier to look at this one. How do I get from 3 to 36? Tyrell? Let's see if it works. Is 1.5 times 12 18? Click, click, click. Yes, it is. Is 4 times 12 48? Yes, it is. There's my relationship. Okay? My voltage is 12 times my current. That's what it says. Voltage is 12 times the current. Use the equation to determine the voltage when I have 6.2 amps. Because is 6.2 on my graph? No, that's over here somewhere, right? The voltage is 12 times 6.2. And if I do that on my calculator, I get 74.4 volts. Okay? If I gave you a voltage, could you find the current? Sure. Just divide it by 12. Now, talking about what you guys did in grade 9, here's a relationship. Mr. Ohm was the first guy to figure this out. Back in René Descartes, did they even have electricity? They didn't even know what it was. Your great-great-grandparent didn't even have electricity. Okay? And you kids are just siphoning it for free, charging your iPods in my classroom. That's a relationship between voltage, current, and the resistance in the circuit. How do we find out the resistance? Well, look at this. V is 12I. V is, let's just rearrange that, RI. Does that glaringly jump out in front of you, showing you what R is here? What must R be? Got to be 12. That's the resistance. 12, that's the symbol for ohms. Okay? So we're just going to get that definition here now. Discrete and continuous. Okay? Current and voltage, that was continuous. Intermediate values had meaning. Okay? Is it possible to find intermediate values? Here it makes sense. Okay? It doesn't just, like the current doesn't just jump from 1 amp to 2 amps to 3 amps. You can go gradually from 1 to 2 to 3, back down to 0. It just depends, right? We were talking toothpicks. It didn't make sense. Okay? Those are called discrete. So just a couple of examples. Here's a good way to figure it out. This is good. Ask yourself, can I take half of it? Okay. Can I take half a toothpick? No. Discrete. Can I take half of a person? Well, you can, but it's kind of cruel. It's called war. No, you can't. It's discrete, right? And then sometimes you can take half of it. So then you ask, well, can I take smaller increments of it? Does that make any sense? A quarter of it? I'll show you what I mean in a sec. Okay? Classify each of these as discrete or continuous. Time taken to complete a 100-meter sprint. What's the world record? Anyone know? Is it? Couldn't possibly be in the 8s yet, could it? I don't know. I don't follow it, but I know that dude from Brazil, he's pretty fast. Yeah, that's him. 9.7, maybe 9.6 something. Okay? So he does it in, I don't know, let's call it 9.7. It depends, like if it's a real record, they actually test the wind. Okay? No, you had too much of a tailwind. Can't count that one. Too much of an advantage, right? If all the conditions are right, If it's at the Olympics or a world event, then if it's recorded properly, down to the thousandths of a second, they might take that. Okay, is there a guy, can I take half of that? Time. Is there someone somewhere who got 9.8, do you think? Over the last, sure. Is there someone somewhere who maybe got 9.75? Sure. Is there someone somewhere who got, like me, like 19 seconds? Sure, right? Can I cut a half of it? Can I cut it in a quarter, take a quarter of it? Yeah. Time is always, always, always continuous, right? In some sports now, it's so competitive, like skiing, they have to go past hundredths of a second because people are tying. There's a tie for second and third because they got 1 minute 47.62 seconds. They have to go to thousandths now. Isn't that amazing? 2 skiers come down a hill and they got exactly the same time. You got a tie for second. Well, who's third? Well, nobody. Now you got a fourth. There's no third. Like, it's amazing, okay? Time is always continuous. Always, always, always. This applies to you guys. How many of you will pass Math 10? I already said this. Does half a person have any meaning? No. Out of 28 of you, 28 will pass. Maybe 27. Maybe 26. Maybe 25. Hopefully no lower than that. Okay, but this is definitely discrete. I can't have half a person. And I know you're going to say, well, you know, doesn't the average family in Canada have 1.6 kids? Yeah, that's true. What 0.6 of the kid do you want? The top half or the bottom half? Okay, that's an average. It doesn't really, you know, it doesn't make any sense, right? Either you have 1 kid or you have 2 kids. Discrete. Height of students. Let's say the average was, I don't know, I'm going to use imperial stuff, 5 foot 6 inches. Is there a kid out there who is 5 foot 7? Sure, for sure. Someone is 5 foot 8? Absolutely. Is there someone in between 5'7" and 5'8"? 5'7" and a half? Sure. Is there someone in between 5'7" and a half and 5'8" somewhere in the world? Absolutely. Is this discrete or continuous? Continuous. Yeah. Okay? Somewhere, somehow, I'm going to find someone in between someone else's height. I can take half of an inch. Or if you like it in centimeters, fine. Same thing. Now here's the tricky one. Shoe size. What size shoe are you, Brianna? 6? Okay. Alicia? Oh. 8.5. Is anybody 9? Who? She's proud of it? She's not Japanese, is she? Your mother didn't band her feet in bandages to keep her pretty? Okay. I don't know why I say these things. Okay, so someone else is an 8. Someone else is a 9. You can take half of it. But if you got, my feet are in between, like, and it depends on shoe sizes, I know. Sometimes you get a Nike and they're 10 and they fit tight, and then you get a 9 from Brooks and it's big. There's no standard. They don't get audited. But if you're 10, you got a choice. If you're 10.25, you can pick this one or you can pick that one. That's your 2 choices. So in this country, they're discrete. Having said that, what if you go to China and get some custom shoes that are like twice as good as your Nikes and they cost like $6? It's continuous, isn't it? If they're custom, there would be a size between 10 and 10.5. So I hate this question. It's both. It's neither. You can make the argument either way. I know the answer would say discrete, because in this country, either it's 8 or 8.5. That's it. That's your 2 choices. But there is custom shoes out there, right? Okay. That's it. 1, 2, 4, and 6 to 12.